Section 7.1, we're going to look at the idea of a sampling distribution. All right, so some vocab we got to cover first. Statistic and parameter. So a statistic is a number that comes from a sample, all right, whereas a parameter is a number that comes from a population. So if I ask a sample of 30 Patriot High School students what their favorite lunch is, and 60% say popcorn chicken, that 60% is a statistic. If I were able to ask every single Patriot High School student, whatever percent said that popcorn chicken was their favorite, that is a parameter. Okay, so we want to make sure that we know these symbols. These are the most common ones. Okay, so we know this is mean, P is population proportion, and then sigma is the standard deviation. So we have looked at all these. These are things you may have seen, but if not, we need to make sure we know them. So X bar is a sample mean versus a population mean. P hat is how we say this because it's got a little hat on there, is the sample proportion, and then SX is a sample standard deviation. Okay. So we have an example here. We want to identify the population, parameter, sample, and statistic. So the Gallup poll asked 515 randomly selected U.S. adults if they believe in ghosts, and out of those 515, 160 said yes. So let's identify those four pieces. Okay, our population is going to be all U.S. adults. Okay, we asked a sample of 515 of them. So the population that we are trying to represent there is all U.S. adults. Okay, the statistic, the information that we have, because it came from a sample, we would say that P hat is the proportion in the sample who say they believe in ghosts, which is 0.31. And then the parameter would be the proportion of all U.S. adults who believe in ghosts, which we don't know, okay, because we weren't able to ask everyone, but that is the parameter that we are trying to estimate by using the statistic from this sample. Okay, so I want you to pause, read, give this one a try. Okay, hopefully your answers look something like this. All right, the population is all of the times, the parameter is the true minimum temperature, and then the sample is the 20 that we looked at, and the minimum temperature in the sample was 38 degrees, so that is a statistic. Okay, so important note for FRQ. Okay, we want to make sure that when we define parameters or statistics, okay, that we are very clear about what we're talking about. Okay, so anytime we're talking about a parameter or a population, we want to make sure we use like the word all or true. That way it makes it very clear that we are not referring to the statistic, but we're referring to the entire population. Okay, way you remember it, the letters match. Statistics come from samples, SS, and then parameters come from population, so P and P. All right, makes it easier to remember. Okay, so a sampling distribution. Okay, we've already kind of talked about this in this class, but we haven't given it this term. Sampling variability, okay, is the fact that if I take a different sample from the same population, I might get different values, okay? So if I take a sample of 5 students and ask for their height, and then you take a different sample of 5 students and ask for their height, we might have different average heights, okay, because our samples vary even though they come from the same population. So this is kind of an illustration of this. This is taking samples of 5 from pennies and then recording the year that the pennies were made. This is called a sampling distribution, okay? It is all of the possible sample sizes or possible samples that we could take from the same population. So we have this group of pennies here. This is all of the different combination of 5 pennies that we could pick. And then we found the average year that those pennies were minted. Okay, so it is all the possible sample sizes of whatever size we picked. All right, all the possible samples from that population, and then we find some statistic, mean, proportion, range, standard deviation, doesn't matter what it is. We find some statistic for every single possible sample. All right, so most of the time we're using a computer to do these things, but when we work with very, very small populations to sort of give you the idea of what the computer is actually doing. So John and Carol have 4 grown sons, and here we have their heights in inches. All right, and so we're going to look at what is a sampling distribution. So first thing we're going to do is we're going to define our sample size. So our sample size is n equals 2. Okay, we're taking samples of 2 out of their 4 sons. So what are all the different ways that we could do that? All right, so we list out the heights. If we take a sample of 2, so I could take the first son and the second son, the first son and the third son, the first son and the fourth son, and so on and so forth. So there's 6 different ways that I could take groups of 2 from those 4 sons. All right, then we want the mean of each of those samples. All right, so each group of 2, I'm going to find the mean. Okay, and we put that on a dot plot, and that is called the sampling distribution of the sample mean. Okay, a lot of words. We're going to talk about the vocab at the end, but you want to make sure you use all of those words. I know it sounds crazy, but this is the sampling distribution of the sample mean. Okay, it is a dot for every single mean of every single sample that we could take from those 4 sons. Okay, so we can do it with mean, we can do it with any statistic. We're also going to do it with the range. Okay, so I take my list of samples, I find the range. Okay, I subtract the 2 numbers for each of them, and then I put those numbers on a dot plot. All right, so this would be the sampling distribution of the sample range. Right? Why is this important? Okay, if we know what the sampling distribution looks like, if I know all of the possible means that I could get from a population, all right, then it helps me determine whether or not my result could have happened by chance or if there's some sort of anomaly going on here. So we have an example. I want you to pause and read because I don't need to read to you. So I want you to pause and read through this example. Okay, so first question is, do we have evidence that less than half of the chips in the bag are red? Well, we do have evidence, okay? She picked out 20 of them, and only 7 of them are red. That's 35%, which is less than 50. Okay, what we need to know is whether or not this is convincing evidence. All right, so there's 2 possible explanations for how she could have gotten only 7 out of 20 if truly half of the chips in the bag are red. Okay, explanation number 1 is they really are half and half. Okay, half of the chips truly are red, and this sample of 35% is because of sampling variability. Okay, it's just by random chance because not every sample is going to equal exactly the entire population. That's explanation number 1. Explanation number 2 is the population is not actually 50-50. Half of the chips in the bag are not red, and Mrs. Lynn is lying. Okay, well, how do we know which one is true? So first of all, we would do a sampling distribution. So I zoomed in here so you can actually see it. This graph is if we took 500 different 20 chip samples, okay, and we found the proportion of each of those samples. So we've seen graphs like this before, okay? We just haven't called it what it is before. So this is 500 simple random samples, okay? All right, so one point we want to make sure you understand, we love to ask this question. There's one dot at 0.8. What does this value represent? Okay, remember each of these dots is one sample. Okay, so that one dot at 0.8 is one sample where 80% of the 20 chips were red. All right, would it be surprising to get a sample proportion of 0.35, which is what she got when she actually picked them out? Okay, and justify your answer. And we're always going to justify based on the graph. So if I look at this graph, all right, 0.35 and lower would be all of this area. And if we look, there are quite a few dots. There's lots of dots, right, in that section. So we don't have like a hard and fast rule. We'll talk about that when we get to later. But in general, we're looking at about 5%, okay? So the amount of dots that were 0.35 and lower is way more than 5% of the total number of dots. So no, that's not really surprising. 0.35 happens a lot, even when the population is 50-50. All right, so do we have convincing evidence? We had some evidence because we had a sample of 20 that was way less than 50%, but do we have convincing evidence? And the answer would be no, because 0.35 or lower happens by chance a lot when the proportion is 0.5. All right, we got to make sure that we are being precise with our vocabulary, so we need to look at a couple things. This graph is a population distribution, okay? This is for all of those chips. There's 100 blue ones and 100 red ones, okay? Then we also have what we call distributions of sample data, which means if I take a sample of 20 chips, I might get 12 and 8. I might take a different sample of 20 chips and get 8 and or 9 and 11, right? I can have lots of different distributions of sample data because I can take lots of different 20 chip samples from my big group, okay? If I start making dots of all of those different samples, all right, that is a sampling distribution. And we always say what it is a sampling distribution of. So it's a sampling distribution of the sample proportion. Okay, so lots of different vocab here. All right, population distribution, distribution of sample data, and then sampling distribution. Okay, all of this terminology, these terms are very important. Okay, so we can't just say the distribution in an FRQ situation. Okay, you have to make sure what you call. What is it a distribution of? You have to name the distribution. Okay, so you have to exactly say what it is. All right, when we do sampling distributions, we can have biased and unbiased estimators, right? Because we're taking a sample, so our sample might not exactly equal the population, but we want to know if it's going to give us a good estimate, all right? So we say it's an unbiased estimator if the mean of the sampling distribution is equal to the value of whatever we're trying to find, the value of the parameter. So in this case, we had all of these different dots that are all of these different sample proportions. If I added all these numbers up and divided by the total, if I found the mean of all these proportions, it would equal exactly 0.5, which means that p hat, the sample proportion, is an unbiased estimator of the parameter proportion. Okay. So we did the sampling heights example, okay, and we did the range, and we want to know if the range is an unbiased estimator, okay? So here was our sampling distribution. These were all the different ranges that we found. We're going to find the mean of those. So 1 plus 3 plus 3 plus 4 plus 4 plus 7, okay? And so the mean of the sampling distribution is 3.67. The mean of all of these dots is 3.67, okay? What's the mean of, or what's the range of the population? Okay, well, range is biggest number minus smallest number, so 75 minus 68 is 7. Okay, the mean of my sampling distribution does not equal the actual population parameter, so it is not an unbiased estimator. Okay. Sometimes when the numbers get big, like we don't want to actually sit there and calculate the mean, so we can look at the graph. The graph for the sampling distribution when it is an unbiased estimator will be centered around the population parameter. All right, what does that mean? The population parameter here was 7. The range is 7. Are these dots centered around 7? No. Okay, so range is not an unbiased estimator. If we look at that same example where we did the means, okay, the mean of these four numbers together is 71.5, which would be right here. Okay, if I look at these dots, are these dots roughly centered or approximately centered around 71.5? The answer is yes. So the mean, All right, X bar, the sample mean, would be an unbiased estimator of population mean. All right, and then last thing we're going to look at, it's helpful to use something that's an unbiased estimator, right? But even with an unbiased estimator, there's still a lot of variation here, right? If my population parameter is like 0.36, 0.37, I could still get one that's as low as like 0.22 or even as high as 0.5. All right, so it's a good start, but any single sample that I take still might not match up with my parameter value. So another thing that we can do to kind of tighten that up is increase the sample size. Okay, these dots up here are sample sizes of 100. Okay, these dots down here are sample sizes of 1,000. So they're still centered around the population parameter, okay, but these dots are a lot closer. There's a lot less variability because I increase my sample size. So just general statistical rule, when in doubt, larger samples are better. Okay, and that's it for 7.1, guys.